Okay, so we have previously seen the calculation of pH, POH, and the dissociation of acid and base. Here, in this slide, we also show that strong acid and the weak acid differences. The first one, the example A, it shows that monoprotic acid, that after dissociation, it becomes totally dissociated and produce equal amount of hydrogen, that's proton, and the conjugate base of that acid. Here, strong monoprotic acid, those acid that dissociate fully or completely, and monoprotic, it means that compound or acids that can give only one proton, they can donate only one proton. For example, nitric acid, HCl, they are all strong monoprotic acid because they can donate only one hydrogen. And weak monoprotic acid, that will be dissociated very slightly, or very small amount of it will be dissociated. That is called the weak monoprotic acid. And the monoprotic acid, weak monoprotic acids, example will be acetic acid, CH3COOH. It is a weak acid and can donate only one hydrogen ion. Okay, so for an example here, it says that calculate the pH of 1 times 10 negative third molar of HCl solution. So since we know that HCl solution, HCl is a strong acid, it's a monoprotic acid and a strong monoprotic acid, so it will dissociate completely and it will produce equal amount of hydrogen as well. So in our solution, we will have 1 times 10 negative third molar of hydrogen ion. And from there, we can find the pH easily because pH is negative log of hydrogen ion concentration. So we can just find the pH from this equation. Another one for barium hydroxide. Barium hydroxide is a base, right? Because it can donate hydroxyl ion. It donates hydroxyl ion. So it is a base, but another thing is it is 1:2 reaction, 1:2 order. Like one barium, if the barium hydroxide get dissociated in the solution, it will produce one barium, but two hydroxyl ion will be produced in the solution. So if we if we dissociate these two, there will be two hydroxyl. From 1 molar will produce 2 molar, 2 molar will produce 4 molar. So that means if I have 0.020 molar, I will have 0.04 molar of hydroxyl ion in the solution. Okay. Here it is, showing is nicely that 2 moles of hydroxyl ion will be produced per 1 mole of barium hydroxide solution. And then POH can be found easily from this solution, like we see it before. POH plus POH is 14. So from there, POH can be calculated, pH can be calculated easily from that solution. So if we want to see, or if we try to see the Ka and the weak acids strength, we will see that Ka, the stronger the Ka or the acid dissociation constant, the stronger the acid. So of course, obviously for weak acid, the Ka will be reduced. And we can actually show this by some equation, by using some equation. If we see the dissociation of an acid in the water, or ionization of the acid in the water, in water, acid will be dissociated, produce a hydronium ion, or we can just simplify it, a hydrogen ion H plus and the conjugate base of it. And if we see, this is the simplification of this. And if we want to see the constant of the dissociation constant, that is Ka, we will see that this is the ratio between this product of hydrogen ion and this conjugate base over the undissociated acid in it. So from this equation, we can also relate that if this hydrogen ion and the anion is larger, is much bigger, the Ka will be increased. That means acid will be stronger. That means more hydrogen ion is available in the solution. But if it is Ka is not big or very small amount, that means these two are not enough, not a lot in the solution, but this one is a lot in the solution. That is why Ka will be reduced. So we know that Ka reduces, the acid strength reduces. For this, using this knowledge, we can find the pH of weak acids and weak base, of course. So for first example, we'll see the weak acid pH. We will try to find the pH of a formic acid, and we know that formic acid is a monoprotic acid and it is also a weak acid. So as for all weak acid, it does not get dissociated completely. A partial amount, a small amount of the formic acid will be dissociated in the solution. And that is why we have to construct an ICE table. That means initial change and equilibrium. What will be the concentration in initial change and concentration of the solution? So what is the Ka of this solution will have, the acid, that this acid, what will be the Ka for this acid if we use this 0.1 molar solution of that acid? Well, Ka does not depend on this molarity of the solution. It depends on the temperature, but for it, we try to see what will be the Ka for this formic acid of this solution. Here we will construct the ICE table, but for this, one information it is given here is that the pH is given. So from pH, we know that pH is negative logarithm of the hydrogen ion concentration. So from there, we can also find the concentration of hydrogen ion. We just take the anti-log of the pH, so we will find the hydrogen ion concentration. So this is the 2.39 is the pH of that solution. We just take the anti-log of this, that means 10 power negative 2.3. This is the concentration of hydrogen ion. And we know this is the hydrogen ion concentration of the solution at the change. All right. So what will be the equilibrium concentration of the hydrogen ion in the solution? Right. So we started with 0.1. We started with 0.1 at the beginning, and at the beginning, let's say 0 seconds. So acid did not have a chance to get dissociated. So there was no hydrogen, no format ion. But when it changed, that means this amount of hydrogen ion was produced, and so if it get produced, it must have been produced from here. So it will be deducted from this original concentration of the solution. So we deduct this original concentration from that original concentration that has been produced in the solution, and that is why it has been deducted. That is why it is negative sign. It is why it is negative sign here, but they get produced. So we put positive sign. And as I said that it is a monoprotic acid, it is a monoprotic acid. So they will be equal amount. That means 0.1 mole will produce 0.1 mole of hydrogen ion. So 4.1 times 10 negative third moles of hydrogen ion produced from exact same mole of formic acid. And then at the equilibrium, we have this balance for this acid. At the equilibrium, we have this balance, but equilibrium, we have this amount of hydrogen ion in the solution. right? So now we can construct the Ka equation. That means this concentration times this concentration over this concentration, right? So hydrogen ion times formate ion over formic acid concentration, the initial concentration of that solution, equilibrium concentration of the solution, sorry. So we will put the values that we found from that table, and here at the end we find that the Ka is 10 negative 4 times 1.8, or 1.8 times 10 negative 4. Of course, it has been taken from the exact values of that we found from this ICE table. But if we have this value of Ka, and we know this is the concentration of hydrogen ion that was produced during the change, or at equilibrium, this amount of hydrogen ion was there in the solution. What will be the percent ionization of the solution? The percent ionization is the ionized acid concentration at equilibrium over the initial concentration of acid times 100%. So for previous example, 4.1, right? 4.1 times 10 negative third over 0.1, because 0.1 we started with the formic acid solution, times 100%. So this one will be the percent ionization of formic acid for that solution. All right. So this is actually we find the percent ionization in this way. Okay. So now we have seen this for monoprotic acid. This is one hydrogen will be produced for monoprotic acid, and the 100% release. So for strong acid, it's considered that whenever from the very beginning, whenever it is in the solution, the 100% will be dissociated. 100% will be dissociated of this, right? And for weak acid, at the beginning there will be a high percentage of dissociation, and as time passes by, the ion of the acid will get reduced. All right. Now, there's another example. It says the pH. Calculate the pH of the solution when there is calculate the pH of the solution when, where is my cursor? Sorry. Okay. It says that pH of the solution when there is 0.03 molar nitrous acid we have. So again, the Ka of the nitrous acid is given, fortunately. So from there, we know that since Ka is 4.5 times 10 negative 4, we understand that this is not a strong acid because this value is quite small, right? 10 negative 4th. So that means it's a very small value. And we immediately understand that, okay, this acid is not a strong acid. So we have to find the ICE table as well, but unlike the previous time, it's not our change are not given. So arbitrarily, we just consider that X amount has been dissociated, and since it's the monoprotic acid, X amount, exact same amount of hydrogen and same amount of nitrous ion will be produced as well. And from equilibrium, at equilibrium, we just have to deduct from this from this, and here they are getting added up. Because here at the initial it was 0.00, so the balance is X only, but here we started 0.036, so X is deducted from there, or X is get dissociated from here at the change. During the change at equilibrium, there will be X molar less than the original that we started with. Okay, so now we already have seen Ka value is 4.5 times 10 negative 4th from the reference, or it is given in the question. So we just plug these values here We just plug those values here, and we take this equation. After this, we find that the equation will be in this form, right? So now here we will have a problem here because 0.036 minus x is creating a problem. So we can just approximate that since it is a weak acid, they do not dissociate fully, right? Or very small amount of them get dissociated. So 0.036 minus x is actually a very small amount. This x is very small amount, so it is almost equal to the same value. They are not getting any appreciable amount dissociated or deducted from it. So we just consider that, okay, 0.036 minus x is almost same to 0.036, right? So with this approximation, we just consider it that the x is this amount. We get x is this amount, and x is this amount. So this 4.0 times 10 negative third molar is the hydrogen ion concentration. So it is the hydrogen ion concentration because x in our equation we've considered that this is the hydrogen ion concentration. X is the hydrogen ion concentration and also nitrous ion concentration. Okay, so we will just take the negative log of this concentration, okay, of this concentration, and then we will find the pH of the solution. pH of the solution by taking the negative log of it. But the problem is that we have considered this is our approximation method. We consider that 0.036 minus x is actually 0.036, but this is approximately, and whether our approximation method is valid. Really, can we just consider this for every time or not? So we have to validate this concentration. If it is more than 5%, it is not valid. We have to go and find exact value, not by approximation, exact value of it. So we try to see the approximation, percent ionization, and we see that is 11%. Actually, it is 11%. So it's more than 5%. It's more than 5%. And now, since it is more than 5%, we cannot consider is this approximation is valid. So our approximation is not valid. And if we just calculate the pH from this value, it will be wrong. It will not be correct one. So we have to go and find the exact pH for this. Hydrogen ion concentration for this. So from here, if we from the previous equation, if we multiply both sides, we will get this binomial equation. Okay, sorry, quadratic equation. We'll find this quadratic equation, and we know that this is the formula to find the x or root of quadratic equation. That is, root is equal to negative b. Negative b is the second one. Sorry, b is the second term of the equation. Plus minus, it should be minus also here. Plus or minus root over b square minus 4ac. 4 is the numerical value. A is here, the first term, A, and C is here. 1.6 times 10 negative 5 is C. So this is A, this is C, and this is B from this equation. So if we put this value in the equation, we will find two roots. One is positive, another is negative, but molarity cannot be negative, right? So molarity cannot be negative. So this value will be discarded. We will discard this unreasonable value. That is less or unreasonable value. So we just discard this value. Okay, so this is actually by not approximation method. So this is actual value of hydrogen ion concentration. So this is the actual value of X. that is the hydrogen ion concentration, and from there we find the pH of the solution, and this will be the correct one. So if anybody just take the approximation method and do not validate it, they will have a chance that they will not get the full marks. Okay, what is the pH of 0.4 molar ammonia solution? Now there is no information given. There is no other information are given, but we know that ammonia is a weak base. What is happening? Sorry. So we know that ammonia is a weak base, and it does not dissociate fully in the solution as well. So we have to create the ICE table as well, and we find that 0.4 molar ammonia is started with. We just arbitrarily say that, okay, negative X amount has been dissociated from here, and X amount of ammonia has been produced, and hydroxyl ion has been produced. Okay, ammonia is the base, so it will be hydroxyl ion, not hydrogen ion, and ammonium will be produced from there with the reaction with the hydrolysis of ammonia. Ammonium will be produced here. Okay, and now at the equilibrium we have, this is the value that is left, and X, both X and X of hydroxyl and ammonium has been produced. All right. Now the Kb, because this is the base, so base dissociation constant. Sometimes students just write Ka or Kb, they confuse with this, so don't be confused with this. If it is a base, it will be Kb. If it is an acid, it will be Ka. So Kb of ammonia is ammonium concentration times the hydroxyl ion concentration over the ammonia concentration, and from here we find this is the equation it stands for us at the end. If we just plug in these values K and then this one is here, this is the equation we will get. So now if from the equation we use the approximation method, because we know that ammonia is a weak base and only small amount of it will be dissociated, and then we just consider that the whole number is still the same. From there, approximation method, we find that X is about 2.7.10 negative third. And for this case, we consider that, okay, this is the concentration of ammonium ion, which is from the previous slide. We have seen that we considered X is concentration of ammonium ion, and also the same for hydroxyl ion. This is same for hydroxyl ion because it is giving 1:1 ratio, the stoichiometric ratio for ammonium. And then, so from here, we know that we have X amount of hydroxyl, or this amount of hydroxyl ion has been produced from there. And okay, this is from the previous slide, we have seen that this is the base dissociation constant. So we just use this for this equation. And we, of course, have to test the validity of our approximation since we approximately use them. And we find that the percent hydrolysis or validity is less than 0.5, which is valid. So we can consider it is correct, our approximation method. So since we have already seen that the concentration of hydroxyl ion is this, so POH we can find just like pH, negative logarithm of this hydroxyl ion, so negative logarithm hydroxyl ion, and we find this is the POH of the solution, right? So pH is 14 minus POH, or pH plus POH is equal to 14. We have already seen it from the previous slide, that POH plus pH is equal to 14 all the time, right? So this is, we know that from this equation, we can find this is the pH of that solution. Now, there is a real problem or example that it says that ionization equation of the three different acids are given below, and from all of these example, we see that all of them are acid because they are producing hydrogen ion. They are producing hydrogen on each of them, and the Ka value for each of them are given, right? And we see that the Ka value for dihydrophosphate is very small amount, right? It is the lowest among all of them. Bicarbonate has -7, it is -8. Bisulfate has a -2 of the constant acid dissociation constant. So from here, we understand that this acid is the weakest among all. This one is the weakest among all of these three. So of course, it will produce the lower pH even if we take the same concentration. Let's say that we take 1 molar of this, 1 molar of this, 1 molar of this bisulfate, but only the biphosphate, dihydrophosphate, will produce the lowest pH of the solution because of the weak of the acid is. And now it says that the concentration of acid identified like 0.015 molar. Find the pH of the solution. What will be the pH of the solution of the weakest acid that has been identified from the question number, previous question. So we found out that H2SO4 is the weakest acid among all, and to find the pH of the solution, we have to find the ICE, right? ICE table, like initial concentration is 0.015 concentration, and change we do not know. Let's consider it's X, and then it will produce one hydrogen. It's produce one hydrogen, and then it is X, and the phosphate ion also will be produced one, so it will be 1X. For this case, we know that there are two hydrogen, although, but only one hydrogen ion will be produced at the beginning. After that, maybe there will be a second ion, proton donation. But for this case, we consider pH1 and PO4 3, and it is -3. It will be. All right. So for this, after that, we have to find the concentration because Ka is already given in the previous slide. So from here, we can find by approximation method. Of course, we have to validate whether approximation method is true. If less than 5%, only it will be valid. If not less than 5%, we have to find by the using the quadratic equation of that equation. So from here, we understand that the relative strength of conjugate base and acid, the higher, the stronger the acid, the higher the Ka. We already have seen it. And interestingly, if the acid is the high, the Ka is very high, its conjugate base of it is the lowest. The base strength of that acid is the weakest. So if the acid is very strong, its conjugate base will be very weak. If the acid is very weak, its conjugate base will be strong. So this is inversely related to each other. Now, if we want to see the Ka and Kb of conjugate acid-base pair for weak acid and weak base, and for our convenience, if we see the case study of if we see the dissociation of weak acid and weak base for this, we have seen this equation previously. That is the acid dissociation, that hydrogen and its conjugate base is being produced from here, and we can express the dissociation constant by Ka. We know that it will be equal to this concentration of hydrogen ion and concentration of this conjugate base over Ha. But since it is a weak acid, this this A will further go for hydrolysis because it's a weak acid. So the base of weak acid usually go for hydrolysis, further hydrolysis in the water. So this conjugate base will go for hydrolysis, and because it's a base, so it will produce the hydroxyl ion. So it will produce hydroxyl ion further, and then we can express this as Kb, the base dissociation constant. But at the end, after this, if we just sum these two things up, then this undissociated acid from the both sides will be cancelled out. This A, that is the conjugate base, and this A, this is something, will be cancelled out from the equation as well. and at the end, we will have this hydrogen ion and hydroxyl ion and this water. So this water is coming from here and this hydrogen ion and hydroxyl ion. So there should be a relation between this Ka and Kb since it is coming from these two equations, right? So this is the equation, the relation between Ka and Kb, that is the product of Ka and Kb is always the Kw, that is the water dissociation constant. Of course, it differs from temperature as well. So from here, we understand that we can find the Ka or Kb for any weak acid or weak base if we know the temperature, the water dissociation at this temperature. So from here, if it is Kb is given and Kw is always constant at some temperature, so we can find the Ka and also inversely for Kb as well from the same similar way. We can find the Kb. And of course, if the Ka is higher, the higher the Ka, the stronger the acid, or the higher the Kb, the stronger the base is. Okay, so another example, it says that consider the following two acids and their ionization constant, that this formic acid, it has a 10 negative fourth, and this hydrocyanic acid, it has a 10 negative 10. So from here, we understand that this is a weakest or weaker among these two because this is very small. And the stronger, weaker the acid, the conjugate base of this will be stronger. From here, we see that from the previous example, we saw that the formic acid, it was stronger. The formic acid was stronger from the previous, and it has a 10 negative 10 4. Yeah, the conjugate base of it has a Kb of 10 negative 11. However, hydrocyanic acid, we saw it from the previous example that it is the Ka is 10 negative 10th, but its conjugate base has a strength of 10 negative 5, which is much higher than this format ion. So it is much stronger base. Okay, so it goes in that way. If the inversely is true, if the base is strong, its conjugate acid will be weaker, or inversely related or true as well. So now, so far we have seen that conjugate acid, the different definition of acid and base, Arrhenius definition and Bronsted-Lowry definition. There is another way we can define acid and base as well, and that is the Lewis way, and this is this name came same after the G.N. Lewis, which we have already seen the Lewis structure previously. So it says that if any compound or any substance that can accept one lone pair, not one electron, but one lone pair of electrons, so it will be considered as an acid. For the first example, example A here, it says that this boron trifluoride, although we have seen this is exception of octet because it does not fill up the octet, only have a 6 electron as the outer shell. Sorry. So it can take one pair of electron from ammonia, and that is how it acts as an acid. And ammonia, of course, is a base. So it will take this electron, and this is actually a dative bond that is called the dative bond because these two electrons are coming out from this ammonia, and it is usually represents as a arrow from where it is coming. The electrons are coming. Another example B, is carbon dioxide, CO2, is able to take one pair on lone pair of electron from the oxygen atom in water, right? So the water, the oxygen in water, it will have two lone pairs of electron. It can give one lone pair of electron to carbon atom in carbon dioxide, and this is how the carbonic acid is formed. Of course, afterwards the electron will be replaced or changed from here to there to form a stable compound. But this is also by definition, this carbon dioxide is an acid because it is taking one electron from water, and water is acting as a base here by donating one pair of electrons. Okay, so now we have seen so many of the key formula and expression for this, and all of these will be helpful for us to understand the pH, to find out the Kw value, and then from this Kw we can find the Ka values, and from there we also can find the equilibrium constant for any equation, and from thus we can find the pH or pOH of the solution as well. Okay, so the rest of it will be discussed in lecture 3. Thank you for listening. Hope you have wish you have a good day.